For more than a century, physicists have been chasing one of science's most ambitious goals, a single framework that explains everything, from galaxies drifting across the cosmos to the jittery, unpredictable behavior of subatomic particles. General relativity elegantly handles the first category, describing gravity and the geometry of space-time. Quantum mechanics flawlessly governs the second, predicting the behavior of particles with uncanny precision. Yet the two theories, powerful as they are, don't fit together smoothly. Trying to combine them is like forcing mismatched puzzle pieces that almost, but not quite, line up. So, where do we begin unraveling this contradiction? Surprisingly, with a simple idea: vibration. In everyday life, we're accustomed to quantities that vary smoothly. You can drive half as fast, then half again, and repeat infinitely. But at tiny scales, nature refuses to behave like that. Energy, momentum, charge, they come in fixed increments. They're quantized, which is where quantum physics gets its name. This seems strange until you compare it to the behavior of a vibrating string. Pluck a guitar string, and only certain standing wave patterns can form. 1 hump, 2 humps, 3, never 2.5. The string allows only very specific resonances, discrete, not continuous. Now imagine everything in the universe being made of unimaginably tiny versions of these strings, each vibrating in allowed patterns. Suddenly, quantization becomes natural, not mysterious. This isn't just poetic metaphor. A vibrating string can be represented mathematically as a combination of sine waves. Add enough sine waves together in the right proportions, and you can create any waveform. You can also break any complex waveform apart into its underlying components. This flexibility gives such a model incredible explanatory power. Every particle we observe might be nothing more than a unique vibrational song of the same underlying object. And here's where things get interesting. Those vibrations behave exactly the way quantum particles do. Combine the right wave components, and you get a sharply localized spike, much like a particle appearing at a specific place. Spread the components differently, and you get a smooth wave, much like a particle smeared out over space. The notorious uncertainty principle drops out naturally. When waves are spread out, motion is well-defined but position is fuzzy. When waves are tightly concentrated, motion becomes ambiguous. It's a compelling picture. But if vibrating strings explain so much about quantum behavior, can they also explain the structure of matter itself? Or even the origin of space and time? If waves create particles, then where exactly do particles come from, and how do they acquire all their unique properties? If matter is ultimately nothing more than vibration, then particles, the building blocks of atoms, should emerge naturally from the complex interplay of waves. And remarkably, they do. Imagine multiple waves overlapping at a single location. When their peaks reinforce each other, you get a sharp, well-defined spike, the signature of a particle. When they cancel, the spike disappears. This idea not only echoes Einstein's insight that mass is a form of energy, but also explains why particles can be both localized and spread out. But this wave-based picture reveals something even more profound. Uncertainty is not a flaw in our measurements. It's built into the fabric of reality itself. Consider a wave that oscillates smoothly and predictably. It stretches out across a region, making its momentum easy to determine. But precisely because it's spread out, the location of its particle is ambiguous. Now combine many waves of different wavelengths. They interfere, sharpen, and create a narrow crest. Now the location is precise, but the momentum becomes the messy sum of many components. The more waves you add, the more sharply you define position, and the more chaotic the momentum structure becomes. This interplay is the uncertainty principle in its purest form, arising naturally from wave mathematics. But there's an even stranger consequence. A particle, in this model, is not a tiny marble traveling through space. It is a momentary meeting point of many waves that briefly converge and then drift apart. After that convergence, the waves spread out again, meaning the particle dissolves back into uncertainty until the next interaction forces reconvergence. This beautifully matches the behavior seen in the famous double-slit experiment. A single photon leaves a source, spreads out as a wave, passes through both slits simultaneously, then recombines and behaves like a single particle when detected. The convergence of waves at the detector is what we interpret as the particle arriving. The model feels alien because our world is made of stable patterns that seem solid. But the quantum world isn't solid, it's rhythmic, dynamic, musical. Particles are fleeting notes played by the universe. Yet this wave picture, elegant as it is, cannot describe everything. It doesn't yet tell us why particles move the way they do, or how they experience time, or why they can become entangled across vast distances. To push further, we must examine how waves, and the strings that carry them, interact across space and time. Shifts to a new frontier, quantum communication, and the race for unbreakable security. For centuries, every encryption method, from Caesar's simple letter shifts to modern cryptographic algorithms, has shared one vulnerability. If someone figures out your key, your secrets are laid bare. Today's digital world relies on enormous computational complexity to keep those keys safe. Modern encryption works because brute forcing the key would take so long that no hacker could realistically pull it off. But this protection is a race against the growing power of computers. Every increase in computing capability tightens the noose around conventional encryption. And looming on the horizon is a threat many governments fear: the arrival of full-scale quantum computers. Quantum machines exploit qubits, objects that can exist in multiple states simultaneously, to test huge numbers of possibilities at once. A code that would take a classical computer thousands of years to crack could, in theory, fall to a quantum computer in minutes. This realization triggered a global search for new forms of security, and it led some researchers to embrace physics itself as the solution. Enter quantum key distribution, or QKD. Rather than relying on mathematics to secure a key, QKD uses the strange behavior of quantum particles. A key is encoded in the states of photons sent from one location to another. And because observing a quantum particle inevitably disturbs it, any interception attempt leaves a detectable trace. If the sender and receiver see signs of tampering, they discard the key and try again. In principle, this makes the distribution of encryption keys unhackable. But there's a catch: photons are fragile. Sending them across long distances without disturbing their quantum states is extremely hard. That's where satellites come in. High above Earth, in near-perfect vacuum, photons can travel freely without bumping into atoms. And recently, a tiny experimental satellite proved this concept spectacularly. The result electrified the global cybersecurity community. It suggests a future where banks, governments, corporations, even individuals, could transmit keys that no hacker can intercept unnoticed. It hints at a coming era of digital privacy that borders on absolute. But is the dream as perfect as it sounds? Quantum keys may be unstealable, but does that actually make encryption unbreakable? And what happens when quantum computers become powerful enough to brute force everything else? Dives into the hidden weaknesses. Quantum key distribution solves one problem, interception, but leaves another wide open. Once you receive a key, you still use it to encrypt and decrypt messages in the ordinary, classical way. A hacker doesn't need to steal the key if they can simply brute force the encryption itself. And that is precisely what powerful future quantum computers threaten to do. A classical computer tests keys, sequentially, one by one. A quantum computer can evaluate vast numbers of possibilities simultaneously. Suddenly, an encryption algorithm once considered safe for thousands of years might crumble instantly. Governments are fully aware of this danger. Agencies like the U.S. National Institute of Standards and Technology have already sounded the alarm. Encrypted data harvested today may be cracked a decade from now. Hackers can store encrypted financial records, medical files, corporate secrets, waiting for the first affordable quantum machine to unlock them. To counter this, researchers are racing to develop post-quantum cryptography, algorithms that remain secure even against quantum brute force. Many rely on mathematical structures that resist efficient quantum shortcuts. Lattice-based cryptography, for example, creates complex multidimensional mazes where the key is hidden somewhere inside. There is no known quantum algorithm that can find the solution faster than a classical machine. This means the future of cybersecurity may not rely solely on quantum physics. Ironically, the strongest defenses against quantum computers may end up being very clever classical algorithms. So where does that leave QKD? It turns out QKD is not a magic shield. It protects keys in transit, but not the encrypted data itself. And widespread adoption faces another challenge. If a malicious actor simply performs constant interception attempts, a quantum network could be forced into endless restarts, creating a new type of denial-of-service attack. The reality is far messier than headlines suggest. Quantum tech promises unparalleled security, but also introduces new vulnerabilities. The encryption landscape is shifting into a two-front war. physics versus mathematics, photons versus algorithms, quantum attackers versus quantum defenders. The winners will determine the future of privacy. But encryption isn't the only frontier where quantum physics reshapes our understanding of reality. What about consciousness itself? Next dives into one of the most provocative questions in modern science. At first glance, consciousness seems like a simple fact of existence. You're aware, you experience things, you think thoughts. But try to define what consciousness is, and the mystery deepens immediately. Is it the product of electrical signals in the brain? A feature that emerges from complexity? Or something more fundamental, woven into the fabric of matter itself? To approach this question, we must first examine what consciousness looks like from inside the brain. Billions of neurons exchange electrical impulses every second. Patterns of activity correlate with memory, perception, decision-making, and emotion. But correlation isn't explanation. Even if we mapped every neuron firing in your brain, would we truly understand the experience of being you? Researchers attempt to make sense of this through competing theories. One influential idea, the global workspace theory, compares consciousness to a mental spotlight. Many unconscious processes happen behind the scenes. Your brain tracks your posture, balances chemicals, and analyzes visual input long before you're aware of anything. Consciousness arises when information becomes globally accessible, entering the stage of awareness. Another model, integrated information theory, claims consciousness is simply what happens when information becomes richly interconnected. Any system with sufficient internal influence, biological or artificial, should possess some degree of subjective experience. Under this view, consciousness is graded, not binary. Even simple systems might possess faint glimmers of awareness. Both theories raise uncomfortable questions. If consciousness is a matter of information flow, could machines someday exceed us? If it depends on complexity, where is the threshold? Does a fish possess it? An insect? A bacterium? And what about matter even smaller than that? This leads to a startling possibility. Perhaps consciousness is not something the universe produces, but something the universe contains at every level. Could awareness exist, however faintly, even down at the scale of electrons and quarks? Next part explores the provocative idea of quantum-based consciousness. If consciousness emerges entirely from physical processes, then we should be able to trace those processes downward to their most basic ingredients. Neurons fire because ions flow. Ions flow because electrons move. Electrons behave according to quantum laws. So where exactly does awareness begin? Does it suddenly appear once enough neurons fire together? Or is it something far more pervasive? This is where some physicists and philosophers entertain a controversial idea, panpsychism, the notion that consciousness, in some primitive form, exists in all matter. Not that atoms think, but that they possess the tiniest spark of subjectivity. Just as complex patterns of waves can create particles, perhaps complex patterns of information create minds. Quantum physics fuels this speculation. In phenomena like superposition, a particle exists in multiple states until observed. But what counts as an observation? A conscious mind? A measuring device? Interaction with another particle? We still don't fully understand why superpositions collapse, and some interpretations hint at a link between measurement, information, and awareness. Consider cases like blind sight. Individuals who are clinically blind can still navigate obstacles unconsciously. Parts of their brain process visual data without their awareness. This suggests consciousness is not simply a matter of sensory input, but of which information gets elevated into subjective experience. Could something similar happen at smaller scales? Could particles respond to their environments in ways that hint at proto-awareness? The idea is speculative, but intriguing enough that figures like Roger Penrose have explored potential quantum contributions to consciousness. Whether or not panpsychism is correct, it forces us to confront a key philosophical dilemma. If consciousness is not fundamental, then where does it come from? If it is fundamental, how does it combine to create beings like us? We're left with questions far stranger than the answers. But if consciousness feels mysterious, quantum physics has an even more mind-bending surprise waiting. Experiments suggesting information may influence the past. Next we dives into the quantum eraser.
To understand the quantum eraser, we must first revisit one of the most shocking discoveries in physics: entanglement. When two particles interact in just the right way, they become linked so that measuring one instantly reveals information about the other, even if they're separated by light years. Einstein famously rejected this, calling it spooky action at a distance. He believed particles carried hidden instructions, defining their properties long before we measured them. But John Bell found a way to test this idea. His insight was simple. If particles did carry hidden instructions, the statistical correlations between their measurements should obey strict limits. But if quantum mechanics was correct, if particles truly didn't decide their properties until measured, then experiments would violate Bell's limits. Decades of tests later, the verdict is clear. Quantum mechanics wins. Entangled particles do not behave like classical objects carrying preset properties. They behave like two parts of a single system, no matter how far apart they are. And their coordinated behavior happens faster than light could possibly carry information. Does this mean faster than light communication is real? Not exactly. Quantum randomness prevents us from sending useful messages. But something undeniably strange is happening beneath the surface of reality. And we're not done. Another experiment goes further. What if a particle's behavior depends not only on what happens now, but on what will happen in the future? That is the haunting implication of the delayed choice experiment. By deciding after a photon has entered an apparatus whether or not to keep or remove a critical mirror, researchers found that the photon's earlier behavior changes accordingly. Insert the mirror, and the photon behaves like a wave. Remove it, and it behaves like a particle, even though the decision happened after it passed the critical point. It's as if reality waits for us to decide what experiment we're performing before choosing a history that fits. But the real jaw-dropper comes next, an experiment that erases information from the past, changing the outcome after it should already be determined. Concludes the journey. The quantum eraser experiment pushes delayed choice to its limit. It begins like the classic double-slit experiment. A photon travels toward a barrier with two openings. If nothing marks which slit it passed through, the photon behaves like a wave and creates an interference pattern. If we tag the photon's path by giving each route a distinct marker, the interference disappears, replaced by a pattern showing two distinct particle paths. So far, so familiar. But here's the twist. What if you erase the path information after the photon has already passed the slits? Engineers designed an apparatus where entangled partner photons are used as a kind of record. One photon goes through the slits. The other travels elsewhere to a detector that can either preserve or erase the witch path information. And the result is stunning. If the witch path information is erased after the first photon has already hit its detector, an interference pattern mysteriously appears, retroactively. If the information is preserved, the interference vanishes, again, retroactively. It appears as though the future measurement determines whether the past photon traveled through one slit or two. Does this mean time can run backward? That we can send information to the past? Probably not, but it does reveal a profound truth. Quantum events do not obey our classical notions of time and sequence. The universe does not commit to a definite history until all relevant information is settled, even if some of that information comes from the future relative to the event. This challenges everything we assume about causality, reality, and the flow of time. Rather than a fixed sequence of events, the quantum world may behave like a network of correlations existing outside time as we understand it. What we call the past may be less rigid than we think. If the universe only chooses its history when we observe it, then what is reality before observation? And what does that say about the role of consciousness in shaping it?